welcome back to the NPTEL lecture series on bioelectricity. So, we are into the 8th lecture, and previously we have talked about the action potentials and the minus 90 millivolt potential difference across the membranes, and we briefly talked about the different ion channels, and I promised you that I will be coming back to the ion channels once I kind of talk about the different techniques which are being used. So, today what we will do, I will introduce you to the basic techniques which are being used for recording the electrical properties of the excitable cells, and from there we will move on to the properties of the ion channels which have been discovered in that whole process. Okay. So, let us start with the historical perspective, how the electrical measurements of the excitable cells have taken place. So, before we kind of move into the electrical measurements, so one of the fundamental thing, the way bioelectricity person treats a cell is that it treats a cell just like an equivalent circuit model. So, essentially it is like this. So, for example, okay, let's this is our lecture 8. Lecture 8. Okay. So, bioelectrical measurements. Bioelectrical measurements. Right? Now, the way a cell is being treated is something like this. So, I have already told you that cell is a bilipid membrane like this. Okay? Like this, and then in between you have the series of membrane proteins sitting like this, channels, membrane proteins likewise, and then you have something like this. So, this is a kind of a and you have this cholesterol molecules and all those things which are sitting there. So, essentially this barrier across, so this is indicating your outside the cell, and this is inside the cell, and we have already discussed about the different molar concentration, millimolar concentration of the different ions. So, you can treat this membrane first of all as a capacitor. So, this is the symbol of capacitor. So, essentially the way to treat it as a capacitor arrives from the point. So, if you look at the membrane like this, and if this is part of the membrane with a lipid bilayer, and this is inside shown by I and this is outside shown by O. So, inside it is negatively charged with respect to outside. So, these are the negative charges, and outside it is positively charged. So, it is almost similar to a parallel plate capacitor. So, if I connect a wire like this out here, and I connect a wire like this out here. So, this is one of the ways how you can treat the cell. Similarly, you can treat the cell in another way. You can consider this as a battery. So, essentially what you see is that across this, if you call this positive and you call this negative terminal. So, if I show you blue, okay, this is the negative terminal and negative wire. Fine. This is another way to treat the cell. And apart from it, the motion across, something like from here, things are moving like this. Okay. So, basically things move like this, okay, or things moves like this outside. So, the movement of the ions across this faces some form of a resistance. And you can put this as a resistance component. Fine. So, now you add all of them together. Okay. And here you can call this as a plate like this, parallel plates like this. So, essentially what you did is, and call it outside or extracellular, and this is your intracellular. So, essentially what we did actually, we treated the cell as an electrical circuit. It has all the three basic components. It has a capacitance across its membrane, just like when we treat it as a parallel plate capacitor. It has a resistance which ensures or creates an obstruction or occlusion to the flow of ions across this membrane, and it functions as a battery. So, if you translate this whole thing into a single diagram, it will be something like this. You can treat the cell. This is extracellular side, E, or outside the cell. You have the capacitance, you have the resistance, and you have the voltage across it. So, this is we call as electronic model of the cell or electrical model of the cell. This is also called equivalent circuit model. Now, this equivalent circuit model, as it is in front of you, now you can treat the cell accordingly. You can measure capacitance, you can measure resistance, you can measure the voltage, and of course, the current flow across it. And the thumb rule in this game is V is equal to I R, where V is the Ohm's law, where V is equal to potential difference, I is your current flow, and R is your resistance. Okay. So, now just the same way we draw the equivalent circuit model. Now, what I will do, I will draw a cell and I will show all the different kind of measurements which are being followed and the challenges and how far we are by 2013. So, before I start this, let me tell you that these kind of measurements are treating the cell as equivalent circuit. Likewise, even much before all these circuit components were discovered, the discovery or evidence of bioelectricity was pretty much there. As I mentioned earlier, also from the time of Volta, Galvani, all these things were there. It was never formalized. It took a while. It was during the last century that everything kind of got formalized, because by that time there is a formal field of electrical engineering which was there. So, everything was kind of structured. So, what we see during last century, apart from the development in terms of semiconductor, high-end amplifiers, miniaturization of electrical devices, and very sophisticated, good measurement techniques. Apart from all these things, what we see, the whole field of bioelectricity is slowly getting formalized, because it is kind of discrete event all over the place, and there is no standard really one textbook by where you can cover all the whole spectrum of bioelectrical phenomena. So, over the period of time, at different centuries, different time, people have different kind of experiments. Now, slowly we are trying to understand that these are very, very fundamental events which are regulating our day-to-day events of our life. Okay. So, coming back now. So, the first sort of recording which were followed. say for example, I consider this as a cell. Okay. Now, if I poke an electrode like this out here, one electrode like this, and this electrode is connected to a voltmeter out here, and the voltmeter, the other end of the voltmeter is connected to another electrode which is outside like this. So technically I can calculate, because I am treating this as a battery, so I can calculate the voltage across the cell. So that's where repeatedly I am telling you, with respect to outside, inside is negative and this is minus 90 millivolt, or it varies from minus 70 to minus 90 millivolt. Simple measurement. Second thing, if instead of a voltmeter you have an ammeter sitting there, then what you can measure is, if there is a movement of sodium, likewise you should be able to measure the current across it. And indirectly what you actually measure is, you measure the, because of this you measure the change in voltage. That's what you exactly measure. So whenever we talk about an action potential, what you are measuring here is the, on the scale, this is 0 and y-axis. Okay, this is showing you the time, and this is the volt in millivolt. So what you essentially measure is this. This is where the electrode is measuring the influx of the sodium. Likewise, if you compare this, this is what you are measuring. Now, this kind of measurements what are being done falls under, so measurement techniques could be now classified into two groups. The first group is called extracellular recording. The second group is called intracellular recording. So these are the configuration of recording system or recording electrodes. So let's first distinguish what is the difference between extracellular recording and what is the difference between intracellular recording. So the word itself indicates when the electrode is outside the cell, that is called extracellular recording. When the electrode is inside the cell, it is called intracellular recording. Okay. So here electrode is, if I represent electrode by E like this, okay. So in this situation, and if this is the cell, then the electrode is something in this position with respect to outside. Here you have the measurement. Okay. So it is inside the cell, but the second configuration is out here like this, and your electrode is outside the cell with respect to your whatever measuring device you have, and there is an electrode at a distance. This is the other configuration. So if I go back into the previous one, what you see here, this kind of action potential traces and falling down likewise, what you see here is coming from intracellular electrodes. Okay. Intracellular recordings of AP showing action potential. So even the previous slide, so this is a classic intracellular recording. But then what will happen in an extracellular recording? So coming back, so now let's see this situation. So in the next slide, what I will do, I will kind of highlight this one in the next slide. So, let us put the cell like this. So, this is the base. So, for example, this is the base. On this, here you have a cell sitting like this. And now you have two options. Imagine electrode is either sitting underneath like this on the surface, or you can have, I will show the other configuration on the other, and you have another electrode which is the electrode at a, this is the electrode sitting. And on top of that, this is the cell. This electrode is connected to a voltmeter right here, and the other lid of the voltmeter is out here at a distance. And this cell is in an extracellular fluid like this. It's bathed in a fluid. When the cell is sheeting an action potential, what we essentially see is there will be an influx of sodium ion from all over the place. Like this. So, sodium is moving in from outside. Okay. So, this sodium movement essentially will, for a very small fragment of time, will make the electrode which is sitting outside to feel as if it is becoming negative, because from this surrounding. So, to show it like this, if I have the voltage plot sitting here, so y axis showing voltage and x axis is showing time. So, the baseline, I am showing the baseline like this. So, this is the baseline. Okay. Now, as soon as the action potential gets initiated, so there will be a dip like this, because it will experience that particular position, and it will go up and then it will come down. So, this is the zone where the sodium are getting in. This is where the electrode will experience as if locally for a while all the positive charges have moved in, and the electrode, on the top of electrode you will see a slight negative, and then again the ions from the other side will immediately rush in, and you will shoot like this, comes back. And this is how you record the extracellular potential. In this situation, the advantage and disadvantage. So, the advantage is this: you are not damaging the cell. Your electrode is touching the surface. You could have an electrode from top, as I was trying to tell you. You could have an electrode like this sitting on the top, or you could have at the bottom. But the disadvantage is something else. So, the disadvantage is this. So, let us again draw the situation. So, this is the electrode sitting, and one second. This is the electrode sitting, and this is the cell which is sitting on top of the electrode, like this. Okay. Now, out here, so across this gap, so there is always a gap out here. So, we always assume that a cell and an electrode is almost sandwiched over each other. But if you look at the geometry of the cell essentially, so if I take this cell and just take you to a little bit of a biology of the cell, if you look back, the cell is something like this. If this is the cell, on top of this cell surface you have a whole bunch of different kind of proteins, the whole series of proteins which are like this. It is decorated like this. Any cell is decorated like this. it is not a smooth surface as I am drawing it. So, when this cell, now go back to the previous slide. If in the previous slide, now if I add this component, so I am using a different color just to demarcate the difference. One second, let me do something. Okay, let me do something. Let me just change this diagram a little bit. Okay, now let me introduce all the other component on top of it, all the different proteins which are present out here. Okay. Now I introduce the electrode. There. Now if I put the electrode, now see the problem. So the problem is, if you look at it very carefully, you will see a zone which is totally gapped. So that zone, I am just putting it in yellow now. Now this is the zone. See this gap? This gap is the cause of huge amount of leakage whenever we are making a measurement, and this gap is called, technically there is a name for this, and this is called cell electrode interface. The cell electrode interface is one of the critical problem of lot of leakage current which are taking place out here, because this connection or this sandwiching between the cell and the electrode is not perfect, and cell is almost like a sponge structure. So the options are, either we make the surface of the electrode rough. Okay, so it's something like this. So if this is a rough surface, then we make the electrode surface. So I'm now let me represent the electrode surface with the pink color. Okay, so I make the electrode surface something like this. Instead of making it perfect, I make it so that the cell fits on that and kind of along the topographical feature or along the ups and downs and bulges of this electrode, the cell sits. This is one option by which you can reduce the loss of currents out there, loss of ions, loss of fidelity, or improve the fidelity of the signal. There is another way you can do it, which is, the next technique is, you have this electrode out here. You decorate the electrode with molecules. You decorate it with molecules which will bind to the cell, bind to those. So these are the molecules with which you decorate the cell, and now you have the cell out here on top of it. And now cell has its own proteins like that, which I am showing in blue now. Okay, so that way you reduce the gap in the cell electrode interface. This is another way of doing it. Okay, so there are several groups which are trying to develop different kind of antibody-like molecules which will bind the cell, hold the cell much more tightly on top of the electrode. There is another technique. Other technique is that you push the cell on top of the electrode with some kind of gel, some kind of a hydrogel or some kind of a cryogel or some kind of a gel. You push it down. So it is something like this. What you are trying to do is, let me pick up a totally different color. Okay, I think this is good. So you are creating some kind of a gel out here which will put sufficient pressure from the top. So you are putting pressure like this. and since it's a gel-like structure, it is not going to damage the cell. So essentially what you are doing is that you are creating a mechanical pressure which is pushing the cell down. These are the different challenges, what I showed you now, of doing a recording using extracellular electrode. But there are several advantages. Now let's enumerate the, since we have talked about the problem of cell electrode interface, let's talk about the advantages. First, no damage to cell. No damage to cell. Second, long survival of the cells on electrode. Of the cells on electrode, just I am showing by E. Then you can do all the chronic experiment or long-term experiment, okay, of related to drug discovery and everything. This is a situation when I am talking to you about when you are doing the recording outside the human body on a culture dish. But what will happen when you have to implant this extracellular electrode inside the body? This complicates it little further. This is a situation, let's imagine, say for example, let's pick up some tissue. Okay, let's think we are talking about a brain tissue like this. Okay, so this is the, now you want to implant an electrode here, fine. So if, say for example, this is your electrode which you have implanted. Now the problem arises when the electrode is out there is something, a real life problem. Here this electrode is interacting. So first of all you have to philosophize what all the challenges this electrode is going to face. First of all, this electrode is in a dynamic ionic system. In the dynamic ionic system, first of all, electrode material should be so inert that it does not get corrugated or does not get damaged because of the ionic milieu, because there are a whole bunch of sodium, potassium all over the place, chloride likewise. Second thing, a cell is a dynamic entity. So a cell continuously secretes certain things in and around it. So if I had to kind of amplify this image, it will be something like this. If at the cellular level, what is happening? So there are a lot of cells like this sitting here, and likewise these are the cells, and okay, and you have an electrode out here like this. Fine. So now this electrode which is sitting here is experiencing all the ionic fluids and the extracellular secretion of secretions of the cells. Okay. So what we really mean by extracellular secretion is something, say for example, this is your cell and this is your electrode. Now this cell is continuously secreting different kind of molecules, and these molecules essentially what they do, if this is your electrode and this is your cell, these molecules will eventually plug the connectivity between the electrode and the cell, and thereby you are losing upon the signal what the electrode is supposed to receive all the time. So you are realizing that extracellular recording or implanting extracellular recording for stimulation, so these have multiple purpose. In vivo situation, these are implanted into the brain for stimulation, for say for example for let's enumerate them, for spinal cord injury, or any kind of which is in short it is called SCI, for any kind of other neural damage. So these extracellular electrodes, I am just putting EC as extracellular electrode, are used for stimulation, electrical stimulation. But they are, the problem is that initially they are all fine, but over the period of time, because of all the different situation I told you, narrated you, their efficiency to transfer the signal reduces. The fidelity of the signal is being compromised. Same thing happens when you grow cells on top of electrodes. And some of the devices which are used by the drug industry are called, for such things are called planar microelectrode array. Planar microelectrode array. These planar microelectrode arrays are nothing but simple, say for example, a backlight sheet on which you have a bunch of electrodes which are on the surface, and there is a well where you can grow the cells on top of the electrodes and you grow the cells. So I told you there are two situations. You can use that for in vivo, for stimulation and for neuroprosthesis, and there is another situation where you can study the electrical properties of the cell in a culture dish. And it is something like this. If you look at it, if the microelectrode arrays will look like this. Okay. Okay. So it's kind of a sheet like this, on which you will see a series of electrode which are embedded on it like this. Okay, fine. And around this there is a well. Well is something like this. So inside this well, you can actually grow the cells. So you have, let me represent the cell with say blue. So you really can grow the cells like this on top of this. Okay, any kind of cell. And these on these plenary and these electrodes, and of course there is a ground electrode out here. Okay. So each one of these are individual channels, say channel 1, channel 2, channel 3, channel 4, channel 5, channel 6, channel 7, channel 8, channel 9, channel 10. I am just showing you 10 channels just because I cannot really draw. But there are such 64 channel, 128 channel, fantastic microarrays which are available across the world. And here, just before I proceed, there are some individuals' work which I want you guys to look online. Will be please go through the work or of these references. Please go through Professor Bruce Wheeler, in University of Florida, Gainesville. Then should go through the work of Professor Bruce Wheeler, then Professor James J. Hickman should go through some of his work on microelectrode arrays in University of Central Florida, UCF. Then you should go through the work of Professor Gregory Brewer. And then there is one more group whose work I will, in the next lecture I will tell you. There is another very fantastic group in Germany who are doing very nice work on this field. Please go through some of their work. They are really nice pieces of work which you guys will be really interested to look at how the world is moving in this direction. Okay. So coming back. So you actually can, on these kind of planar microelectrode array, and do one more exercise. Go to Google image and look for planar microelectrode arrays, images of the planar microelectrode arrays. This will help you. Okay. So people are developing neural network on top of it. Okay. So they are making something like, like this. There are networks they are forming, and actually you can monitor the signal propagation within such network. So the whole field is really moving at a very interesting pace. So apart from it, there is the second generation of modifications which is taking place, which is basically you are making these arrays which are flexible planar microelectrode arrays. Flexible planar microelectrode arrays. So what you are essentially doing, the base what you are making out here, what I was showing you, you are making this base as flexible base. So they are much more easy, they are not rigid structure. You can really do a lot of measurements on them. Okay. And out here, all the recordings what you are getting are the recordings what I explained out here somewhere. This, all the extracellular recording. Now correlate this structure what is in front of you now, which I showed you in one of the previous slide, with the structure what I showed you. So this is one single electrode, and here what I showed you is 10 different electrodes, and it could be 64, it could be 128, likewise, so on and so forth. Okay. And those of you who are in Indian context, you may refer to the work of Professor S.K. Sikdar, who is working in Indian Institute of Sciences, Bangalore. He also has a very active group out here. Then a few other people. I'll cross check few other people who are there in the field whose work I really will appreciate if you guys go through it. Go online, give search, and see the kind of things they are doing. So what I will do now at this stage, I will close in the lecture today, and we will again continue with a little bit of a microelectrode array, and then we will move on to the next technique, which will be the intracellular techniques. Okay. Thanks a lot.